Hello everyone, I'm Norman Wahlberger. Thanks for joining me on this adventure. We're working towards expanding our number theory from the zero-dimensional case to the one-dimensional case to the two-dimensional world of Maxwell's. And today we're going to look at a very interesting family of numbers, the Bernoulli numbers, which lead ultimately to the Bernoulli polynomials, which are a very interesting family of polynomials that have a big role in analysis, especially with regard to the Euler-Maclaurin sort of summation formula. But they're also involved in lots of different aspects of mathematics. And I want to introduce them to you today in the context of the Faulhaber investigations for sums of powers. And that will lead us to an interesting family of polynomials associated with the name of Faulhaber. So the territory that we're going through here is similar to some things that we've done in the Algebraic Calculus 1 course, and we'll touch base with some of that today. Okay, so the Bernoulli numbers are a famous sequence of rational numbers, actually, not integers, but rational numbers. They were introduced by Jacob Bernoulli, one of the many famous Bernoulli brothers, in a posthumous work of 1713. And he was following the work of Johann Faulhaber, who had previously created formulas for the sums of powers of numbers. And here is something from his work. This is a chapter called Summi Potestatem, written in Latin. In this work, Ars Conjectandi. And what we see here is a bunch of polynomials, and these polynomials are actually the Faulhaber polynomials that Faulhaber discovered, and the final sort of coefficients of every sort of second one of these things are the Bernoulli numbers. And you can see here down in this bottom row, he's identifying some of the first ones: 1/6 minus 1/30, 1/42 minus 1/30. So the Bernoulli numbers are quite unpredictable, and it's quite an interesting story. So let's start by looking at a so-called exponential generating function for the Bernoulli numbers, which is a nice way of introducing them. So I have to remind you about the exponential on series. Okay, so we're going to use the term exp of t to denote this series in t, whose kth term is t to the k over k factorial. So there's a 1 over k factorial in front, and then increasing powers of t. And we're thinking of this as like it's a polynomial or a polynumber that just happens to keep on going. And we're not going to think about this crucially as a function. So in ordinary standard analysis, we talk about the function e to the t, which rests on this number e, which is some infinite decimal, which we actually can't access. Okay, so we're not able to calculate e. We can create a program which will generate more and more digits in a certain direction. But to say that there's this number e that's at the end of the rainbow, that's the result of completing this ongoing algorithm or process is wrong. It's logically wrong. Okay, so we don't have e, and so therefore we don't have e to the t either. So the number e is unfortunately a fiction in pure mathematics, and ultimately that means that anything built up from it is also inherently fictional. Okay, so what we're doing here is I want to promote this idea that we should move away from the function approach to things, where we think of an expression like e to the t or x of t as something which inputs a number, t, and outputs another number given by this infinite sum. We want to move away from that to thinking about this thing as basically a list of coefficients. Okay, it's really the discrete list of coefficients which is at the heart of what this thing is. Okay, and evaluation of such a thing for a given input t is not something that we're interested in doing. Okay, because we can't do it, because there's an infinite number of things to be added up, and we just can't do that arithmetically. So it's an important point that I'm going to have to reiterate over and over again, but this is in the advice section. It's really important that modern students and aspiring researchers adopt this more sensible computational approach to the fundamental nature of these objects which are at the heart of analysis. Okay, so how do the Bernoulli numbers arise from this exponential series? Well, if you look at this exponential series, okay, it starts 1 plus t plus 1/2 t squared and so on. If you take 1 from both sides, then you get x of t minus 1 equals t plus 1/2 t squared plus 1/6 t cubed, etc. So that obviously has a factor of t. So let me just do this up here. So if we consider x of t minus 1, okay, and then we divide that by t, well, then I'll calculate that with a power series in t, okay. So we're going to get this series here. And that's 1 plus 1/2 t plus 1/6 t squared plus 1/24 t cubed. So it's a lot like the exponential, except that things are sort of shifted. So there's still factorials down here, but now the powers are sort of one less than you would expect them to be. That's the effect of things. So what we're doing now is we're taking this series here, which is you could think of it as a variant of the exponential series, and we're inverting it. Or maybe it's better to say we're taking its reciprocal. Okay, because inversion actually has sort of two different kinds of meanings in the world of series. So we're looking at 1 over this. So that'd be t over x of t minus 1. And we're expanding that out. So we're taking, for example, let me just sort of do it naively. Suppose we take 1 over and we just, I'm just going to grab, say, 6 of these terms, all right? Again, and I think about that as another series. If I ask my computer to take a power series for that, then I'm going to get 1 minus 1/2 t plus 1/12 t squared minus 1 over 720 t to the 4th, etc. But at some point there'll be a divergence between what's here and what's there, because I've only gone up to the 6th power and I've disregarded the rest. Okay, so if we sort of expanded the denominator here to include more and more of these terms, then we would get more and more terms that would be in agreement with this series here. Okay, so this is the series that we get by taking 1 over this series here and forming a power series for that. And the Bernoulli numbers are appearing as coefficients here, but this is what's called an exponential generating function, which is a little bit of a variant in that there's a k factorial in the bottom here in the denominator. So we're writing this as the summation of bk over k factorial t to the k. All right, and that's the series that you get by taking the reciprocal, basically, of this series here, formed from the exponential by subtracting 1 and dividing by t. So when we compare the coefficients here to these b sub k's over k factorials, then we can evaluate what these b's are. And b sub 0 is 1. Okay, b sub 1 is minus 1/2. b sub 2, well, it's like this 1/12, but you have to multiply by 2 factorial. So that's 1/6. b sub 3 is going to be 0 because there's no t cubed term. In fact, there's no t to the 5th term, no t to the 7th term. In fact, all the subsequent powers here, interestingly, are gone. Okay, there's only coefficients of even powers of t after this place here. However, there's a difference right here. Here's the only sort of odd power of t, this minus 1/2 t, that's responsible for b sub 1. Okay, so then the pattern carries on. So we're really only interested in the even coefficients. B sub 4 is minus 1 over 30. B sub 6 is 1 over 42. B sub 8 is minus 1 over 30. B sub 10 is 5 over 66. B sub 12 is minus 691 over 2,730. B sub 14 is 7 over 6. B sub 16 is minus 3,617 over 510. B sub 18 is 43,867 over 798. B sub 20 is minus 174,611 over 330. Okay, so this is a highly unpredictable sequence of rational numbers. Highly unpredictable. And in fact, it's it's not known. There's no closed formula for these things. One can't just write down a formula for the nth one, okay? But I will say something about computing these things. So the first thing that we should observe here, as we've already done, is that the odd Bernoulli numbers after the first one are 0. And it's worth noting that this b sub 1, which for us is a minus a half, because that's how we obtained it here, this is sometimes... well, there's some variant here, okay? So sometimes there's a variant used where b sub 1 is actually a half, okay? And so sometimes to distinguish these two different possibilities, we talk about b sub 1 plus being a half and b sub 1 minus being minus a half. There's actually good reasons for considering both of these cases, so it sort of depends on the application. Certainly if we start like this, then we get a minus a half to be consistent with this formula. But in other cases, as we'll see, this other one also figures. So why are these numbers sort of interesting? Why do they appear in analysis? K, and then you sum the numbers 1 to the k, 2 to the k, 3 to the k, up to n to the k. So that's going to be then an expression that depends on n, which turns out to be a polynomial in n. Okay, this is a polynomial s sub k. And so maybe we could say this is to be a polynomial s sub k in n of degree k plus 1. And the Bernoulli numbers arise from Jacob Bernoulli's formula for Faulhaber's sums of power. So Faulhaber created these polynomials, discovered them up to about k equals 17, and then many decades later, Bernoulli came along and expressed them sort of more succinctly involving these Bernoulli numbers. So here's his formula for the Faulhaber polynomials. So I sub 1 to n, I sub k, the sum is 1 over k plus 1, and then the Bernoulli number b sub j, and multiplied by a power of n to the k plus 1 minus j. So this sort of starts with n to the k plus 1, and then sort of reduces one at a time as j is increasing from 0 to k. So let's have a look at some examples. When k equals 1, okay, then s sub 1 of n is the sum just of the sum of the natural numbers. I equals 1 to n of I. And okay, the formula that we all know is that it's 1/2 n times 1 plus n. It's like a triangular number. But Bernoulli's formula says that we should take 1 over 1 plus 1, sum from j equals 0 to 1, minus 1 to the j, and then the binomial coefficient 1 plus 1 choose j, times b sub j, times n to the 2 minus j. So when j is 0, well, then we get a 2 choose 0, which is just 1, times b sub 0 times n squared. And when j is 1, well, we get a minus sign, and we get 2 choose 1, which is 2. So 2 times b sub 1 times n to the 1. So, all right, so then you plug in b sub 0 is 1, so that's just a single n squared, and b sub 1 is minus a half, so this becomes just plus 1. We get 1/2 n plus n squared, which is the usual thing that we know. When k equals 2, s sub 2 of n equals the sum of the squares. The formula is that it's 1 over 2 plus 1, sum j equals 0 to 2 now, minus 1 to the j. Now the coefficient 2 plus I choose j, b to the j still, and multiplied by n to the 2 plus 1 minus j. Okay, so we get 3 terms. Here's j equals 0, b0 n cubed. Here's j equals 1. We get minus 3b1 n squared. And here's j equals 2, 3b2 n. You plug the values that we know, b0, b1, and b2. So b0 is 1, b1 is minus a half, b2 is 1/6. You plug them in, and you get this expression here, which factors as 1/6 n times 1 plus n times 1 plus 2n. Sort of familiar sum of squares formula. And when k equals 3, then s3 of n equals, well, you get 1 over 3 plus 1, sum from j equals 0 to 3, the same expression. So then you end up getting this combination involving essentially the binomial coefficients from the fourth row of the Pascal triangle, so 1, 4, 6, 4, no final one. And so decreasing powers of n. Then you have these other factors, b0, b1, b2, and b3. So those factors are always appearing. First b0, then b1, then b2, b3, but now multiplied by the, the appropriate row of the Pascal triangle, and we have to remember that there's some alternating sign. When k equals 4, again, it's the same kind of story. Now we're talking about the fifth row of the Pascal triangle, 1, 5, 10, 10, 5, 1, with the last one is missing. And each of these coefficients is multiplied by b0, then b1, b2, b3, then b4. There's an alternating sign. Then we plug in the various values of the b's, okay, and we get this series here. And that turns out to have a nice factorization like this. So these are the formulas for S1, S2, S3, and S4. And these formulas here were found by Faulhaber in 1631. Faulhaber was from Ulm, was known as the great calculator of Ulm. He was quite a famous fellow, and probably deserves a lot more fame than he actually gets. He calculated these sums all the way up to S17, so all the way up to 17th powers of natural numbers, and got these big polynomials. And he discovered very interesting and important aspects of them. But he didn't realize, like Jacob Bernoulli did, maybe there's a K here, but anyway, he didn't realize, as Jacob Bernoulli did, that there's a kind of a uniform way of writing these polynomials involving these sort of curious Bernoulli numbers, okay? So the formula is quite attractive at this stage here, but all the complexity, in some sense, is in the actual Bernoulli numbers themselves. And as we've seen, they are rather unpredictable. Okay, so in terms of closed formulas for these things, there aren't any, okay? At least none that are sort of effective. But there are recursive formulas. And the simplest one is this one here, that the sum from k equals 0 to n of n plus 1 choose k, b to the k equals the Dirac delta function n0. So most of the time, this will be 0 unless n is equal to 0. And what this formula allows you to do is to calculate the top bn in terms of the previous ones. So if you know b0, b1, all the way up to bn minus 1, you can use this series to evaluate b sub n. So let me illustrate that with, say, n equals 4. So I'll show you how to calculate b sub 4 in terms of b0, b1, b2, and b3. And the series that we're using is this one right here, that the sum k equals 0 to 4 of 4 plus 1 choose k, b sub k. So that's b0 plus 5b1 plus 10b2 plus 10b3 plus 5b4 equals 0. So that actually, is true. And so if you know b0, b1, b2, and b3, then you can calculate b4 from it. Now, why is such a formula true? Well, this thing here is very much like what we saw before, right? If you look at this expression here, this is very much what's appearing in this series for s sub 4 of n. Okay, it's very much like this, except that the alternating signs have disappeared. So we could sort of get at that by putting in n equals minus 1. If we put in n equals minus 1 here, then we're going to sort of remove the alternating aspect. And if we put n equals minus 1 in here, well, the result is going to be 0 because of this factor. You see there's this factor 1 plus n? In fact, you see this factor 1 plus n appearing there. In fact, it appears in all of these, okay? So there's always this factor 1 plus n. So when we plug n equals minus 1 in here, we're going to get 0, okay? And that's essentially the reason why this recursive relation is there. It's a kind of a consequence of, one way of thinking about it is a consequence of the form of the Faulhaber polynomials and basically Bernoulli's formula. Now, in terms of calculating these b sub n, so you can use this recursion, but recursion can be onerous, especially since you're using more and more terms. So it turns out that the world record for calculating B sub n is held by a colleague of mine. That's David Harvey at UNSW, who in 2008 set the world record. He calculated the 100 millionth Bernoulli number. Okay, and that turns out to be a number with 676 million digits. So if you express it sort of in scientific notation, it's actually a rational number, but you write it out, then this is how many digits it has in scientific notation. And his method involved a modular arithmetic, sort of looking at the Bernoulli numbers mod p for various primes p, and then sort of putting that information together using the Chinese remainder theorem and ideas in that direction. And the previous record was also established earlier in 2008, and that was for 10 million. So that's quite a jump, and that's, I guess, still the current record. So that, shows us that, modern computers are pretty powerful, and, these numbers are big, but they're not that big. And so it's quite a lot of work calculating these Bernoulli numbers, and it's quite an interesting topic. Okay, so now let's try to move to a two-dimensional story. We've identified these Faulhaber polynomials, these S sub k's, as interesting family of polynomials, and we know that their degrees go up one by one. So here's a list of them. There's S1, S2, S3, etc., that we can obtain from, say, the Bernoulli formula. So here, by the way, is the original page from Bernoulli. Okay, so we can sort of compare these coefficients here. I've just basically recorded them right here. Okay, so for example, this number, the sum of the 8th powers is over here 1/9 n to the 9 plus 1/2 n to the 8. You see exactly the same. 2/3 n to the 7 minus 7 over 15 n to the 5th plus 2 over 9 n cubed minus 1 over 30 n. Okay, so also, by the way, note curiously that they don't write n squared. Okay, there's n to the 4th. That's the way we write things, but n squared is just written as nn. A little bit interesting. Okay, so what's our plan? Our idea is that we should try to incorporate these one-dimensional things into a two-dimensional picture. Okay, so we can record this family in a two-dimensional array where I've just basically written down the coefficients in increasing powers of n. So starting with n and then n squared, n cubed, n to the 4th, etc. And I've gone down to the, I guess, the 9th row here. Okay, so let's call this matrix F. And we can observe that the Bernoulli numbers themselves are appearing down this first column of this array F. Okay. And if we want to check, the actual Faulhaber polynomials are what we get when we introduce powers of n. So we can do that just by taking our matrix F and multiplying by this column vector of powers of n. And then we get this thing here. And we can actually factor things just as we're used to. Just factor with one command. And we get these formulas for the factored forms of the Faulhaber polynomials. Okay, so when we do this kind of thing, what we're aiming to do is to try to utilize the matrix algebra from linear algebra to provide new insight. Okay, so we're going to take our matrix F right here, and we're going to take its inverse. This matrix is sort of highly unpredictable because, in particular, there's the highly unpredictable Bernoulli numbers going down that first column. Okay, if you look along here, it's not at all clear what the pattern is, if there is any pattern that's easily statable in these entries here. But that's what we do, right? That's our strategy, is to at least look to see if there is something that happens when we take the inverse. Okay, so here's F inverse. Okay, here's F, just repeat it again, right here. And I'm taking its inverse. And lo and behold, magic appears. Exceedingly lovely magic. Okay? The inverse of this complicated, unpredictable Bernoulli number type matrix is this super regular Pascal-Harriet-like maxil. In fact, it's exactly the Pascal-Harriet Pascal-Harriet maxil, except that the final sort of diagonal of ones has sort of been stripped off. Okay, so we're not getting the full rows of the Pascal triangle. 1, 4, 6, 4, 1. The 1 is in all cases dropped. And the diagonal just now becomes the increasing sequence 1, 2, 3, 4, 5. And also there's a checkerboard pattern of minus signs, as we've come to almost expect in a lot of these situations. So this is more or less the Pascal-Harriet maxil, and it's really an astounding thing. I mean, we should be hugely surprised that by taking this irregular object, looking at it from this two-dimensional point of view, taking an inverse, suddenly the irregularity, the unpredictability completely disappears. So we can think about this now as that we really gained some deep understanding that the unpredictable aspect of this can be viewed as a result of this complicated process of taking an inverse. We're starting with something that's very structured, very predictable. We're taking its inverse, and we're getting something that's highly unpredictable. So this inverse transformation, we see its power, and we see its power in clarifying what's really going on. In particular, suppose that we wanted to extend the Faulhaber polynomials, or maybe the Bernoulli numbers. A very easy way of doing this now is to just expand this very predictable matrix, this Pascal-Harriet matrix here, okay? Expand that to a larger size, and then take the inverse of that, because of course taking the inverse of this is going to give you this thing. So we're going to do that, but before I do that, I just want to mention that this correspondence here also can run the other way. So in one of my algebraic calculus videos, one called Faulhaber's Formula and Bernoulli Numbers, this in the Algebraic Calculus 1 series of videos on Wild Egg. In this video, I explain sort of a derivation of the Faulhaber polynomials, starting with an observation of Pascal and using some linear algebra. So basically what I do is I show that you can create this by first understanding that you can rearrange the sums of powers problem into basically a sum of Harriet summations. Okay, so sort of exploiting the Harriet basis in a nice way that was essentially understood by Pascal. So if you watch this video, and if you're interested in this, I suggest that you do that. You'll see that we can derive the Faulhaber story from this linear algebra point of view, and this is a crucial step. We first get to a system of linear equations that has this as a coefficient matrix, and then inverting that amounts to inverting this matrix, and so we get this thing here. So that's a nice complement to what I'm explaining here today. Okay, great. So now let's increase the size of things, because we can generate these Pascal-Harriet matrices pretty easily, right? Here's just a very simple formula. Just introduce a matrix function Kij, say, equals -1 to the I plus j, and then maybe I minus 1, choose j minus 1. That's going to generate a Pascal-Harriet matrix, and then you can easily sort of strip off that diagonal of ones to get, in this case, so here's a bigger version, all right? So the same thing as I've shown you before, but instead of going just down to the 9th row here, we're going to go down to the 17th row. And now I'm going to take the inverse of this, and that's going to then generate the Bernoulli story further, okay? So let's see what we get. So this is the inverse matrix. And so if we just look down that first column, which is the most interesting, is that we see the Bernoulli numbers expanded. So there's the next few, okay? And in particular, we're now able to read off further or higher degree Faulhaber polynomials pretty easily. Now, a very curious thing happens here. So I was looking at this and comparing just with the values on Bernoulli's table. Let me grab Bernoulli's table, and I will show you. Okay, so there's the table. I'll copy that, let's go back down here. Compare the values. Okay, let's look at this thing here. So I want you to have a look at the sum of the 9th powers. Okay, this row that starts with n to the 10. Okay, so the 1/10 coefficient, a 1/2, a 3/4, a -7/10, a 1/2, and a -1/12. Okay, so let's go to the corresponding row over here. Okay, so there's the 1/10, the 1/2, 3/4, -7/10, 1/2, and -3/20. 1/10, 1/2, 3/4, -7/10, 1/2, -1/12. Hey, wait a minute. That's not exactly the same. So let me actually grab this thing. All right, so let's grab that row. Okay, and I'm going to put it directly adjacent to this thing here. Okay, there it is there. So compare this row that we've obtained now with Bernoulli's row right here, starting with the 1/10. 1/10, the 1/2, yes. The 3/4, yes. The -7/10, yes. The 1/2, yes. But the -1/12, no. We've got -3/20. There's a discrepancy. So there appears to be a, well, let's not say a discrepancy. Let's be honest. It's an error on Bernoulli's table in the row for the sums k equals 0 to n of, maybe I, we were saying before. I equals 0 to n of I to the 9. Okay, so let's actually check this. So G, let's call this something like okay, f of n equals this. All right. So let's just check. F of 1 is 1, yes. F of 2 is 5/13. F of 3 equals 29/16. So these are the sums of the 9th powers. And now let's take the corresponding row. Which one is it? So it's this last one here, right? This is the one with the -3/20. So I'm going to, let's say, find another function, say g of n equals this. All right. And I'm going to calculate g of 1 and g of 2. That's 5/13. And g of 3. That's 20,196. This agrees with the actual summations. So that's telling me that the formula that I've obtained from this linear algebra point of view with the -3/20 here is actually correct. And if we replace this -3/20 as Bernoulli has here with the -1/12, we're going to get the wrong formula. So we see that we benefit not just in augmenting our understanding, but this linear algebra, very systematic point of view, I think it has a potential for sort of reducing errors because we're obtaining these large-scale structures, sort of at a single blow with just a single inverse operation, and we're starting from something which is really very structured. Right, this matrix that we're starting with is given by this very simple formula, so there's not so much room for error. So I hope you've enjoyed this introduction to the Bernoulli numbers and the Faulhaber polynomials, which are very important, and they really should be in every calculus course, in my view. That's why it's important for you to take the Algebraic Calculus 1 course, and then moving to the Algebraic Calculus 2 course, where we're going to be doing a lot more of these sort of on-series kind of activities where we're looking at a power series from different points of view. In the next one, we're going to be looking at the Bernoulli polynomials and trying to adopt a two-dimensional point of view towards them.